Hello, this is Rashid Ansiri, doctor engineer and a technologist in mechanical engineering, and I will try in this video to technologically introduce the elasticity problem. In other terms, I will try to answer the substantial question, what is an elasticity problem? Of course, as simply and as clearly as possible. Okay, let's go. So, the elasticity problem is characterized by the fact that when we have a certain body with a certain geometry, with a certain shape and certain dimensions, and this geometry can be 1D, 2D, or 3D, and this body is also characterized by its mechanical properties, mainly the Young's modulus E and the Poisson's coefficient nu. And when this body is subjected to external forces as imposed loads and external linkages as imposed displacements, it will react, it will answer to these external forces and external linkage, and this answer will be under the form of a stress distribution and a displacement distribution. Distribution here means at any point of the body. When we say stress distribution, means that that there is at any point of this body a value of stress. This stress is internal, it's not external like the imposed loads. This is so an internal stress at any point of the body, and this is there, and there are also internal displacements at any point of the body. It is to note also that the intensity of these stress and displacement distributions will depend on a very important characteristic of this body, of the elastic body, which is called stiffness of the body. And this stiffness depends mainly on the geometry and the mechanical properties of the body. Now I will talk about the von Mises stress criterion. In fact, when we have a stress distribution and we have a considered point in this body, the stress at this point will take a tensor format. A tensor in this case means a matrix format. So you can notice that this stress tensor is symmetric, and the diagonal terms reflects the normal strains, and the extra diagonal terms reflects the shear strain. The problem here is we cannot compare this 3D stress matrix format or tensor format to the body yield strength, which has a scalar format. So in order to overcome this problem, we can use several criteria that permits to transform this 3D stress tensor format to an equivalent scalar format of stress, to an equivalent stress scalar format. We can use for example, the criteria of Tresca or the criteria of Rankine, but when we talk about elastic body, it is judicious to use the von Mises stress criterion. In fact, this von Mises stress criterion permits to obtain an equivalent stress called von Mises equivalent stress using the formula that you see in the screen. You can notice that this formula involves the different components of the 3D stress tensor format. You can notice the normal strains and the shear strains. This von Mises equivalent stress will be easily and naturally compared to the yield strength of the body in order to evaluate the elastic resistance of the body at the considered point. Now I will talk about the resistance criterion. In fact, when we have a stress distribution, in other terms, we have at any point of the considered body the value of the Vomises equivalent stress, we can find the point at which this value is maximum. So at this point we have a maximum Vomises equivalent stress, and as I explained before, this Vomises equivalent stress has a scalar format, so I can compare the maximum Vomises equivalent stress to a certain admissible stress. This admissible stress is equal to the yield strength of the considered body divided by a certain coefficient of security. This coefficient of security depends on the industrial application involving the elastic considered body. So in this way we can evaluate the elastic resistance of the whole considered body. This educational video takes end. I will appreciate all your remarks and your suggestions, and I will answer all your questions in the comments. Thank you very much for your attention.